Well, during the years of research on the heart, these genes are really good candidates to understand why we have genetic defects in the heart. But what we've seen is that there are other genes that are also very important for the heart, that they are not only expressed in the heart, they are not only present in the heart. But it's very hard to study them because they could have effects in other organs as well. So far the research has been mainly concentrating on the low-hanging fruit, if I may say, just to look at the genes that are only in the heart. But what we've done is really to look at more genes that are actually expressed in other tissues, including the heart, and trying to understand why they are important for the heart as well. How do you identify those non-heart genes that could be doing something in the heart? There is a computational trick. So what we've done is when the gene is present in the heart, we ask, why is that gene actually present in the heart? And actually genes have switches that turn them on and off. So what we were looking for were switches in our genome that could turn genes on in the heart. So it doesn't matter whether that gene has other switches that will turn itself on in other organs. What is really important for us is to look in the genome whether that gene has a switch that only turns it on in the heart. That's what we've been doing. We've realized that actually the genes that are really important for the heart have such switches that are only present in the heart, and so we apply that to a whole genome to find more switches that switch on genes only in the heart. So your work has not been done in humans, you've been working with vinegar flies. It's hard to think of something that is less like a human. Can you describe what this process is and why it's an important precursor to understanding better how humans work? So just to put things in context, the problem with congenital heart disease, which is a disease which affects 1 in 100 babies in the world and in Australia as well, is that we don't know which genes are actually causing this disease. 80% of the cases are unknown. We know it runs in families, but still we don't know the genes that are involved. So that's the context. We really needed a rapid way to identify which genes were involved in the disease. So to date, when you do a genetic screening on congenital heart disease, we only know about 100 genes that are involved in this disease, and that is based years and decades of research. So with our new pipeline we have predicted 1,300 of those with just one computational run. So, what we are trying to do is, okay, now we have discovered all these genes, we need to rapidly test them. So how can we find an efficient method to rapidly confirm that the genes that we've predicted with our computing model actually is involved in the formation of the heart and cause disease? So that's why we went to the fruit fly. This is really important basic research that we are doing at Monash because it provides us a new opportunity to really rapidly test genes that are functional in the heart. And we may not know this, but flies do have hearts too, and a lot of human disease has been actually tested in flies, because we have the same organs. Of course there are simpler versions, so that makes sense. But the building block of all of our organs are also present in flies. And then what was really fantastic about the flies is that we could rapidly test whether the genes we've predicted are actually important, so that's what we've done, and we've proven that 70% of the genes that we've predicted actually lead to abnormal hearts in the flies or are really important for the fly. So what's the application of this research then? What do you do if you are identifying these genes? I'm assuming you would eventually use a prenatal screening for it? Yes, so, a word of caution, this is still a long step until because what we've done is really restrict the research space on which are the important genes. We have 20,000 genes in our genome, so we wanted to rapidly identify which ones would be important for the formation of the heart, and therefore might be causing disease. So the next step for us at Murdoch Children's Research Institute is then to screen for patients who might not have a diagnosis before and see it from a research perspective, whether these genes actually had mutations in there as well that could be causing disease. And then there will be other steps then to include this in a diagnosis panel. But what we've done is really to restrict the research space, so we know exactly which genes to look at as novel cause of the disease. So if you were to fast forward some years, how do you hope this work ends up? As I said, we have 100 genes nowadays in screening panels, and that only covers 20% of the known genetic causes. Now we have 1,300 genes, and we hope that in a few years then our diagnosis panel will have these 1,000 genes, and then we can rapidly give an answer